In C++11, the auto keyword has been repurposed to provide type inference. Let's make a working copy of auto.cpp and take a look at how this works. We'll open this up in our editor, and I'm just going to maximize it so you can see the entire file. So I'm including the type info header as well as IO stream because we're using type ID down here. And up around lines 7 through 9, we have 3 variable definitions. We have an integer, a character string using a C string, and a string class string. And then on line 11 and 12, you'll see some new looking stuff. The auto keyword allows you to define a type by the value of the initialization. And so whatever the type is of the initialization, that'll be the type of the variable. So I could say string there, but I say auto because maybe at this point I don't know what it is, or maybe what it is 27 characters prone to error. But this is how it works. And then I come down here and I print out the type ID of each of these. And we'll talk about decal type in a moment here. Let's bring this down to size and compile and run it. And you'll see we get the names of these type IDs. And this will be different on different systems. So these might not look exactly like they do on mine. But here I is for integer. PKC is for the pointer to a constant character, which is what this pointer actually is. It's a constant character pointer. And capital S lowercase s is the string class, and that's right here. Type X is this capital S lowercase s. That's our string type, because I have initialized it exactly the same way that I initialized our string class. So I could actually just type S class here and save that and run it, and we get the same result because that's the type of that. And here I can type cstr here, which is our C string, which is initialized like that, and I can compile and run it, and now it's this pointer to a constant character. Or I can type I here, and it will take on the type of I, which is an integer. And you'll notice that in each of these cases, Y is getting exactly the same type. And the reason for that is decal type. So I'm declaring the type of Y to be exactly the same as the type of X. So I'm using X to infer the type of Y. This is different than if I had done auto Y equals X, because in this case, I'm actually assigning the value of X as well as the type to Y. But in this case, I'm really just assigning the type, and it's an uninitialized variable. So that's a great way to get a type as a type. To get an inferred type as just a type without doing an assignment or an initialization. So these variables are still strongly typed. X is every bit as much an integer as I is, and Y is every bit as much an integer as I is. It's just that finding their type is now being done automatically. So here's a great use for this, and you'll see this a lot. Actually, I'm going to come down here after these so that you can see them more easily. I'm going to say for auto it equals sclass.begin. So I'm creating an iterator here without having to type out the type name for the iterator, which can be very long in the STL. And while it does not equal sclass.end, and increment our iterator. And then I can come out here and I can say cout what's pointed at by it and a space, and just give it another little endl down here. And now when I compile and run this, you see we get all of our members from our container there, whatever type that happens to be. In this case, they happen to be characters. Or I can do this like this, using a new range-based for loop. Very short and sweet and easy to type and easy to read, much less prone to error than the old way of doing this. Now there's one more new use for the auto keyword, and I'm just going to delete this right here. And we're going to type a little template function up here. So this will be a little bit of typing. So we're defining a type template, and it's got 2 type names, left-hand side type and right-hand side type. And it's a template function, and it returns an auto here. this is how you derive or infer the type of that auto return, and it's like this. So we're using decal type here, and it's taking whatever the type of that operator is. And so the plus operator used with whatever those two types are will return a type, and the compiler can figure out what that is without actually evaluating that expression. And so it can figure out what that type is, and then it uses that type in auto. So this is the dash right angle bracket, just like you'd use to dereference a pointer to a structure or a pointer to an object. And that's being added to the syntax of a function here to allow you to use a return type on the right and auto on the left. And this allows you to use decal type. There were problems with how you would parse this if it was on the left. And so they decided to do it this way. And so now we can go ahead and use this template. So we have a template. It's got two different types, left-hand side and a right-hand side. And it simply adds up these two arguments and returns whatever that type is. It could be a third type. It could be one of these types. The template doesn't actually care because it can figure it out like this and then use that type as the return type of the template when it creates its implementation. And so I can come down here and I can say auto z equals and give it two different types. We have a string class and we have a C string. I happen to know that if you use a plus operator with a string class and a C string, you'll get a string class. There was previously no way to write a template that did something ambiguous like that. And now I can say cout z is, and we'll look at z, and cout type of z is, and we'll look at the type ID of z.name, like that. And we compile this and run it, and this is really fun. See, we have this is a string class string concatenated with this is a C string, and the type of the resulting string is a string class SS. So this is something that was actually not even possible with the old way of doing templates in C++. So this new syntax has added something that could conceivably be not just really handy, but make something possible that might have ended up being really, really convoluted otherwise. The new repurposed auto keyword allows type inference for both type declarations and template function return types. This feature may be used as a convenience, as in the case of a for loop, or in the case of a template function return type, to create templates that were not possible before. Now let's delete our working file and run clean to get set up for the next lesson.